On to lecture 9. So here's a tentative list of what we're going to cover in the last parts of the course. So the first thing I want to point out is I added more solved example problems on Canvas. So before there's that PDF solved problems that had, I don't know, like 4 problems in there. So I just updated this with like every solved problem from the entire course. So now there's like, I think 40 or something, so there's a lot more there. So definitely take a look at those. It'll give you an opportunity to practice problems and then check the solutions. So those are there for you if you want extra practice and extra verification. In addition to that, which are solved, so they have the solutions, there's also a list of just textbook problems that are just fun, useful textbook problems. And canonically, these usually end up on exams, so maybe you'll get lucky and solve one that ends up on the exam, but those are also there if you want more practice. Other than that, here are the last 4 lectures. So today we're covering max flow, which is chapter 10 from the book. Then Monday we're doing chapter 11, which is basically advanced graph reductions, which is super important. And then the next Wednesday we'll be doing Turing reductions, which is chapter 12. And then the following Monday we'll be doing approximation and review for the final. And tentatively the final is going to happen on Wednesday, August 3rd. If it's in person. If it's not in person, it won't be in the lecture slot, it'll just be like a Canvas exam. But I'm still waiting to hear on how many people have conflicts before I make it online or not. Okay, so that's the plan. Any questions on that? Okay. So also I wanted to point something out about graph reductions. So we talked a little bit about graph reductions on Monday, and you should have seen them in discussion yesterday. And pretty much I'll also be uploading like a ton of videos, like asynchronous videos on graph reductions, which is why I've kind of been waiting on uploading more videos because they're mostly going to be dedicated to this. So you'll get much more experience with graph reductions. But I wanted to point out how to do graph reductions basically, or in general, how do you use graph algorithms to do general algorithm design. And there's 2 general strategies. So the first one is what we've been looking at, which is graph reductions, which says you're going to black box a known algorithm for solving graph problems. So for the flood flow problem, we black boxed whatever first search. So really we just had to model the problem as a graph, and then we just used whatever first search on that graph to solve the problem. We didn't have to know anything about how whatever first search worked. We just had to know what it was supposed to do. On the other hand, we could modify a graph algorithm. So this is usually called white box. This means you actually have to look at the pseudocode. You have to look at the actual pseudocode of the algorithm and you modify the actual pseudocode. So generally, this would look like taking whatever first search and instead of marking things, maybe you color them different colors because you want to color the graph or something. So that's another strategy you could use. Instead of black boxing the algorithm, you can white box it and actually change the pseudocode to solve whatever problem you're looking to solve. Now each of these has a benefit and downside. Traditionally, it's in the proof of correctness because if you black box something, you don't need to know how that algorithm works, so it's easier to prove it's correct. Whereas white boxing, you have to argue that you're not actually changing the algorithm too much to where it now breaks. So there's benefits to modification too, which is you have more control over what's happening. But ultimately, it comes down to what problem you're trying to solve. Sometimes one is clearly better than the other. Sometimes you do both. I would say most of the times you're going to do both. So usually you'll set up a graph, and then you'll use a standard algorithm like whatever first search, but you'll just slightly tweak it. So you'll say, I'm running whatever first search, but instead of marking the vertices, I just want to do some other process. So usually you'll just do a slight modification. It's not a big deal. And that's an example of where you do both things at the same time. And we'll talk way more about graph reductions later on. We're trying to like slowly get you comfortable with this topic because it's kind of weird. Okay. So, what are flows, which is the topic of this entire lecture? So, here's a story for you. Think of World War II era, and this is a map of Russia. This is an actual map of Russia. And these are rail networks. So you could think of each of these edges in this graph as a railroad, and then each of these nodes are like a station where you drop off or pick up stuff. So in this example here, you could imagine this rail network, this origin here. This is some kind of warehouse with supplies, like gunpowder, food, etc. And the Russians are trying to transport all those resources to this destination over here, which is the bunkers. So that's the goal of the Russians. They want to send as many supplies as they can, as fast as they can. So you could say they're maximizing their rate of sending supply. So that's what's here. You're trying to maximize that rate of sending supplies from the warehouse to the bunkers. And this is called the max flow problem. Now, on the other hand, the Americans, they want to damage as few rails as possible. So they essentially want to break up these railroads here so that that can't happen. They essentially block the movement of these supplies from the bunkers, or from the labs to the bunkers. So that goal, blocking all the possible routes so that nothing can be sent, the supplies can't be sent, that's called the min-cut problem. And these are kind of the two stories you want to keep in your head as we're talking about these problems. These two problems are related. So one involves sending supplies. You want to find a bunch of routes to send supplies quickly, whereas the other problem is about breaking all the routes so that you can't send supplies. Okay? And these problems are related, and we'll see how. This is for dramatic effect. Okay, so here's the formal definitions of the problem. So we have a directed graph, G, and as usual, this is equal to VE. We have vertices and edges. We also have something called a capacity function, C. You could think of this as how much total resource you can send down a single rail. So as you could imagine, rails have physical constraints. You can't just send infinite amount of supplies on a rail. There's weight constraints. There's all kinds of different constraints on what you can physically send. So the capacity function here represents how much stuff you can send at once down a rail. And then you have two vertices, S and T, called the source and the sink. So these are different than the sources and sinks we talked about for directed acyclic graphs, but it's the same kind of idea. A source is where all of the stuff is coming from. This is the main warehouse that has all the supplies, and it's sending all of them. The sink is where all the supplies are going. It's where they're going to finally end up. So conceptually, it's just like in a DAG, where a source has outgoing arrows and a sink has ingoing arrows only. Conceptually, but strictly speaking, these could also have outgoing edges for the sinks in this problem. You just typically wouldn't want to use them. Okay? So now in ST flow in the graph, this is just a function on the edges, and it satisfies this special property called the conservation constraint. So intuitively, what this is saying is the total amount of flow, or the total amount of resources that enters the node V, equals the total amount of flow that's exiting V. So this just says, more supplies aren't magically manifested in the middle of some rail. All of the supplies have to have originated from the warehouse. It also says you're not losing supplies as you're transporting things down the rails, because that would obviously be a problem. So anything that enters V has to exit V. It can't disappear. More can't just appear. And so this is basically the setup for the problem. And the way I like to think about it, if you don't like railroad networks in Russia, is I just like to think of pipe systems. And here you have the source is just anything like a faucet in your home, or it could be a fire hydrant. And all the water is going to originate from this mechanism here, which in this case is the fire hydrant. So all the water in this network comes from the fire hydrant, and it's going to go down different pipes, and eventually it enters into the bucket at the end. And the water could take very different routes to get to the bucket. And each pipe has a physical capacity. You can't send more water in a pipe than it can physically hold. So the capacity here is literally how much water can you fit in a single pipe at a single time. And then the max flow problem is, of course, sending as much water as you can where you don't want to burst the pipes. Whereas the min-cut problem is breaking certain pipes so that no water can get through the system. So in this particular example, this would be a min-cut, or it's just some cut, because after you break those specific pipes, no water can get through the whole network. So any questions on flow networks? What a flow is? It's called the flow because you should think of it as literally water flowing through pipes. Okay? So the key constraint here is this conservation constraint. Otherwise, the flow could be any arbitrary function. It can be positive, it could be negative. You could have negative water flowing. On the other hand, the capacity function is always non-negative, because you can't have a size that's negative. It doesn't make sense. But in physics, there's things like negative current, so those are allowed to be negative. Okay? So now that we know what a flow is, we need to quantify what it means to have a large flow or a large rate of sending flow. And so we're going to define the value of a flow, and we're going to use absolute value notation. This is equal to the total flow leaving S minus the total flow going into S. So in other words, it's the net flow leaving S. And I'm going to use this notation to mean the net flow leaving a node. So in particular for S, this is the formula for partial F of S. That's just the net flow leaving S. And now, okay, since flow always leaves something, so flow leaves a node. So when flow leaves a node, it has to enter a new node. It can't disappear. Because of that, all the flow leaving S must eventually enter T, because that's our sink. That's where things can actually disappear. So because of that, the total flow entering T is also equal to the value of the flow. So when you're computing the value of the flow, you can either look at how much is leaving S on average, the net total leaving S, or you could look at the net total entering T. And these two will be the same because flow can only be created from S, it can only be removed from T, and in between, conservation holds. So any flow that enters the node must leave the node as well. So the flow can't disappear anywhere along the way. Okay? Any questions on that? So there's just a lot of definitions at the beginning. Okay. So now we're going to say the flow is feasible with respect to the capacity function if the total flow on an edge is never more than what that edge has capacity for. So everything up to this point is talking about flows as a general function. It's kind of ignoring the fact that the graph has capacities, but now we're taking the capacities into account. We also say that the flow F saturates an edge if it completely fills that edge. So if you're thinking of water, you put so much water into the pipe that it can't fit anymore. So the flow on that edge is exactly equal to what capacity it can hold. Alternatively, F avoids an edge if it has no flow at all. So naturally, if water doesn't go down a specific pipe, it's avoided that pipe. Okay. So now with all those definitions in hand, we can define the max flow problem. The goal of the max flow problem is just to find a feasible ST flow in your graph that has maximum total value, where the value is the net flow leaving S. So essentially you want to send as much stuff as possible from S while preserving the capacity constraints and preserving the conservation constraints. So the two things here are conservation constraints and capacity constraints. Without those two constraints, you could just send infinite flow. There would be nothing stopping you from doing that. Unless the graph was disconnected. Like if there was no path from S to T, then you couldn't do that. But we're going to always assume there exists some directed path from S to T so that that won't become a problem. Okay? So let's look at an example of a flow. So here in this picture, the flow from one node to another is indicated by the number on the left, so this 10 here. Then the number on the right, that's its capacity. So in this example, we're using 50% of that edge. We're sending 10 units of flow, and it could handle 20 units total. Then the next edge, this one here, we're sending no flow at all. So the flow has avoided that edge. So this is avoided. On the other hand, this edge here, this one's saturated. It's completely full. Okay. And overall, if we just follow the flow, it's going to look like this. And in total, we're sending 10 units of flow from S, and we're also getting 5 plus 5, which is 10 units of flow into T. So the value of the flow overall is 10. So any questions about this picture? So this is a specific flow of value 10, but obviously we could make it bigger, right? So instead of avoiding that edge here, we could just add 1 unit of flow, add 1 unit of flow, and add 1 unit of flow. And now we've created a new flow of value 11. And notice conservation holds because the amount of flow entering this node here, this highlighted node, is equal to the amount that's leaving it, which is 10 plus 1. And similarly, the amount of flow leaving that node, it's still preserved. So whenever you send a path, a unit flow down a path from S to T, that's always going to be satisfying conservation. It's always a flow. But it's not necessarily feasible because it could go over the capacity constraints. So any path any S to T path of unit flow, this will always be a flow. It satisfies conservation, but not necessarily feasible. Make sense? When we send a path, the amount going in and out is maintained. So it's a flow. Okay, if there's no questions, there is a question, yes.
Is the 11 one just better, or can we?
No, that's a feasible flow. So we satisfy conservation because the total flow going in and out is the same for every node. And we haven't broken the capacities, right? So 11 out of 20, that's still good. 1 out of 5 is still good. And then we increase this to 6 out of 15, which is still good. In fact, the maximum flow in this graph, I believe, is over 20. I think you can do more than 20. So this isn't anywhere close to a maximum flow. It's just one particular flow that is feasible in the graph. Okay, so now let's talk about the other problem, which is cuts. So an ST cut is a pair of sets, capital S and capital T, that partition V. And for just to remind you what a partition is, this means that S and T are disjoint, so they don't have any vertices in common, and in total, the union of S and T is all of V. So, like in the picture above, this blue line right here is a cut, and so all of the nodes are either on the left side of the cut or are on the right side of the cut. It completely partitions the set of vertices. And one additional restriction that makes it an ST cut specifically is you need S, little s, the source, to be in the left side of the cut, capital S, and little t, the sink, needs to be in the right side, capital T. Now that we have a cut, we can talk about the value of the cut, which we'll call the capacity of the cut. And what's the capacity of the cut? It's just the total capacity of edges going from vertices in S to vertices in T. So it's this formula here. So in particular, we only care about edges that leave S and go to T. We don't care about the other way around. So if this was S and this was T, you have little s, little t. Then any edges, these green edges, count towards the capacity of the cut. But these edges would not count. We would ignore those in the capacity of the cut. And in general, if there's no edge in the graph, we're just going to define the capacity of that edge to be 0, just so that when we talk about, when we do summations, we don't have to sum over edges, which gets complicated. We can just sum over the nodes. So here I'm assuming that if U to V was not an edge, it'd just be capacity 0. And similarly for flows, we'll always assume that the flow of an edge that doesn't exist is just 0 as well. That's just something, little shorthand we're going to use. So to be really precise, these are technically the sum of all edges from U to V, where U is in S and V is in T. But because of this shorthand, we don't have to make a complicated like set there. Okay. So what's the min cut problem? We want to compute a cut of minimum capacity. It's almost like the name is actually descriptive. So, in other words, this is the cheapest way to block flows from S to T. It's the cheapest way to make sure that no resources can be sent from the lab to the bunkers. So here's an example. So in our graph here, S is in green, T is in the pink, and these red arrows here, these red edges, these are in the capacity. They count towards the capacity of the cut, whereas this back edge here does not count towards the capacity because it goes from T to S. And in total, the capacity is going to be 15. So the min cut problem is kind of easier to state. It's very visually clear. You're just splitting the graph into two sides and looking at the edges that cross from one side to the other. And clearly, if you blew up these edges right here, there's no way to get from S to T, because any way from S to T requires you to go through those edges. So if you remove these, then you kill all paths from S to T. In a sense, you can think of this as two islands, and the red arrows are bridges between the two islands. So once you remove all those bridges, there's no way to get from one side to the other. So you could think of these as islands, and these are bridges. So any questions on the min cut problem? Yes? We're minimizing the capacity of a single cut. So you want to find the cut that has minimum capacity. Cut's a partition of the graph. So we want to pick the sets S and T so that the edges, these red edges, are as small capacity as possible. Yes?
So we're trying to find and plug a bottleneck?
Yeah, this is the bottleneck. So we want the smallest bottleneck so that when we kill the bottleneck, it's very cheap for us. So you could also think of this as the smallest bottleneck. Between capital S, or let me just say little s and T. So in terms of like city roads, you have some roads that are like 6 lanes, and you have some roads that are just 1 lane. Well, it'd be easier to, cause a traffic jam by breaking up 1 lane than 6. So easier to cause a traffic jam by plugging 1 lane road than a 6-lane highway. So yeah, alternatively, you could think of S&T are cities, and the cut is breaking all the roads from one city to the other, so you can't transport between them. Okay, any other questions? So I think the min cut problem is much easier to understand and visualize. The flow problem, obviously, you have this extra function, you have all of these constraints and stuff. But the reason why we care about max flows is because to compute min cuts is actually really hard. But computing max flows is actually pretty easy. So although max flows are more complicated to state formally, solving them will be easier. But ultimately, min cut is really what we want to solve, usually. Okay, so let's talk about how flows and cuts are related. So this is called weak duality. So what this is saying is if you fix any flow that's feasible, and you pick any cut that you want, then the value of the flow is at most the capacity of that cut. So any cut gives an upper bound on the best flow value you could ever get. And there's a special condition for when they're equal. So the condition for when they're equal is F saturates every edge from S to T and avoids every edge from T to S. So if we had a picture here with S and T, we need every edge from S to T to be maxed out. So these are all completely saturated. And we need the other edges going this way to be avoided. So these have zero flow, whereas these have total capacity out of capacity flow. So if that's the case, then this will actually become an equality in that special case. Okay, so why is this true? There's a lot of inequalities, so I'll just kind of go through where they're coming from. So the first thing is the size of F, the value of the flow. This is equal to the net flow leaving S. That's just by definition. And that's also equal to the sum of all the net changes, the net flow for every vertex in S. So why is that? Well, notice that the net flow leaving V is 0 for any V that isn't S or T, because conservation holds. So all the flow going in equals the flow going out, so the net total leaving is 0. So the sum here is we just added zeros to the sum. Okay, the next step, we're just using the definition of what the net total leaving a node is. So we just took that partial F right there and expanded it. So now this step's a little weird. So notice now we're restricting W to not be an S. So why is this? Well, notice that any edge from S to S, so let's say you have U to V. So in the original, that's going to appear here, F from U to V. But it'll also appear in the right-hand side. Specifically when V is U and U is V. So in both summations, F of UV will appear. And so when you take the difference of them, it's just 0. So all of those get zeroed out, and so we can essentially ignore any vertices that are in S for the second sum. So in other words, flow that leaves a node in S and enters a node in S will cancel out, and so we're only left with flow that leaves a node in S and enters a node in T, which is the next step. So that's just because S and T partition V. So we have T equals V minus S. So if W is not in S, it must be in T. It can't be anywhere else. Okay, any questions so far? So far the only important part has been this line, where we've actually used conservation. The rest is just algebra. Okay, so the next part, well, remember, flow values are always non-negative if they're feasible, and we're assuming that F here is feasible. And so this sum is just a negative number. So we can just remove it to get an upper bound. So we're dropping negative terms to get an upper bound. So this thing is at most just the first term, which is the positive stuff. Okay? And now, because again F is feasible, F is at most C. So we're just using feasibility right there. And this, by definition, is exactly the capacity of the cut. Yes? Feasible means that 0 is at most F of E is at most C of E. That's what it means for a flow to be feasible. So it fits inside the pipes, it won't burst a pipe, and it is not negative. So you could think of them as physically realizable flows. You could physically make a flow like this in a physical pipe system. Okay, so the main steps here are we use conservation here to add extra terms, and then we kind of manipulated the extra terms into a form that looked like the capacity of the cut. And then we used feasibility twice to get these last two inequalities. So the last thing is, remember there's the extra condition that says when this is an equality. Well, okay, so these are all equalities, so we only have to look at the two less than or equals. So when is the first one an equality? Well, that's an equality if these are all 0. So if these are equal to 0, it's an equality. And when are those equal to 0? Those are equal to 0 when we avoid edges from T to S. Okay? And then for the second one, when is this one an equality? Well, that's an equality exactly when F equals C, which means we've saturated. So that's when those become equalities. So that proves the second half. Now, what's less important is that you totally understand all the bouncing inequalities. What's more important is that you understand this corollary. So, if I give you a flow F and a cut ST, and you check, and the flow value equals the capacity of the cut, then you immediately know two things. F is a max flow, and ST is a min cut. So it gives you an instant proof that F is a max flow, if you can find that cut. You could think of that cut as a certificate or a proof of the fact that F is a max flow. And why is this true? Well, we know flow values are always less than or equal to cut values. So if they're equal, that means you can't push that flow any higher. It's already hit the upper bound it could ever hit. And similarly, flows are lower bounds on the cut values, so if they're equal, you can't make the cut even smaller. You've hit the lower bound. So this corollary is the important part. Any questions on the corollary? So if your goal is to solve a max flow problem, and you somehow compute a flow, you can check it's correct by computing a cut and checking they're equal. That's kind of what we're going to do, to make an algorithm for solving both of these. So this is the relationship between flows and cuts. You can solve either problem and get a solution to the other one, which is what the next part is about. So not only is this true, so remember this is a conditional statement. It says if you gave me both these quantities, then I know this is true. F is a max flow. But that doesn't mean those have to exist. Maybe in every graph, you have some very small, every flow is small and every cut's huge and they never intersect. But a critical theorem here is there always exists a flow and a cut that are equal in any graph. So you give me a network G, I know there exists a flow and exists a cut that have equal value equal to capacity. So this says that idea we can use on any graph, not just certain graphs. So any questions so far? Okay. So we need to formalize this. This is called the max flow min cut theorem. And it says just what I said before. In every flow network, doesn't matter which one, any of them, the value of the max flow is equal to the capacity of the min cut. So how are we going to prove this? Well, first we're going to modify the graph a little bit for convenience. So we're going to assume the graph is reduced. So in particular, that means if there's an edge from U to V, then there's no edge from V to U. So something like this can't happen. So we don't want things like that where there's basically a cycle between two adjacent nodes. So we can actually break this. We can force any graph to have this property by doing this operation. So we're just going to take these two edges and split them into two nodes. So if you do this, the structure of the graph is the same. You still have the potential to send 7 units of flow from, let me call it U and V. You can still send 7 units of flow from V to U, and you can still send 10 units of flow from U to V, but now you don't have this parallel edges thing. So the structure of the graph is the same. You still have the potential for the same kinds of flows, but now the reduced property is enforced. So in particular, it won't change the max flows in G. So if we create a max flow for the reduced graph, then we can also just collapse the flows on those intermediate nodes, the green ones. We just remove these nodes, and we can get a flow for the original graph. So we're basically doing a reduction here. We're reducing the problem of solving max flow in any graph to the problem of solving max flow on special graphs like this. Okay? You'll see. It's going to be useful in a second. But it is useful, I promise. So this is why it's useful. So we're going to fix a flow, F, and we're going to build something called the residual capacity, CF. Here's the formula. So CF of an edge is going to be the capacity of the edge minus the flow on that edge, if that edge is in the graph. So you could interpret this as the amount of flow you could add to that edge without breaking the capacity constraints. In the second case, if the reverse edge exists in the graph, then the capacity is the flow of V to U. You could think of this as the amount of flow we could remove from an edge. So if you had some edge U to V, then in the residual, so this is U to V, and let's say there's 10 out of 20. Then in the residual, we have U to V is 10, and V to U is 10. So we can add 10 more units of flow from U to V. That's the first case. Or we could remove 10 units of flow from U to V. That's the second case. So this would be CF. And otherwise, the residual flow is 0. So if an edge doesn't exist, we're going to keep it not existing. So the reason why we care about the reduced part is if you had an edge between U and V and the other way, then these two definitions will collide. So this isn't well defined because those two things could be different. So it's important there's exactly one edge from U to V or V to U for this to be well defined. Otherwise, both of these are triggered at the same time, which is a problem. Okay. So that's the residual capacity, and that's how you should think about it. So now we can turn the capacities into a graph. So we're going to define the edges of this graph just to be all the edges with positive residual capacity. And notice that these edges don't have to exist in the original graph. And here's a good example. So here, the original graph did not have an edge from V to U. But in the residual graph, it has an edge from V to U. Yes?
Did you just change that from a greater than or equal, or did you just extend the line?
It is strictly greater than. Yeah, that was a ghost mark. Yeah, we ignore all edges with zero residual capacity. Essentially, any edge with zero capacity, we just pretend it's not an edge. We don't really care about it since we can't send any flow down it. So in particular, the residual graph is not reduced. So we need the original graph to be reduced so that the residual graph is well defined. There's a lot of RE words here. But the main takeaway is now we have this residual graph. So why is the residual graph useful? So here's an example of a residual graph with some flow on it. So this is the same flow from before. It looks like this. So I highlighted in blue all of the edges that have positive flow. So in the residual graph, notice we have a 10 edge and a 10 edge, indicating we can add 10 units of flow to max out to 20, or we could remove 10 units of flow to go back to 0. Whereas for this edge, we can add 5 units of flow to max it out at 5, but we can't remove any flow because there's no flow on it. So that's why the reverse edge is not there. And so on. So any questions on this residual graph? Yes?
So is unused capacity what the backwards edges are?
Backward edges are how much we can remove. So the backward edges are exactly how much is currently on that edge.
Okay, so let's see that draw right there. Could you change it from 10 to 20 to 9 out of 20 so like I can see where the 2...
Yeah. So let me make this 5 out of 20. So we can add 15, or we could remove 5. So edges going in the same direction as they originally were indicate how much we can add to the flow for that edge. And edges that are reversed from what's in the original graph indicate how much we can remove from the flow while maintaining feasibility. Yes? Yeah, so E is indicating the original graph.
But if there is no edge from, let's say, V back to U, the original graph, then we cannot define like the back edge in the reduced graph, right?
So you plug in the backwards one. It's a little weird. So you're going to plug in V to U in this formula, and then that becomes U to V. So the capacity of the reversed edge is the flow on the original edge. It's a little weird, so that's why I like the picture better, because I think the picture kind of demonstrates that better than the math does. But yeah, that's a good point. So the main takeaway, you don't really need to completely get the mathematical formulation, but just think of this picture. We have an edge saying how much we can send in addition and how much we can remove. Okay, so why do we care about the residual graph? So let's assume there is a directed path in the residual graph from S to T. I'm going to call it P for path. And let's define capital F to be the smallest capacity edge on the path. So for example, let's say we had the following path from S to T. This is like 10, 8, 5. Then capital F there will be 5. So intuitively, this is the most flow we could send down that path without breaking the capacity constraints. You could also think of it as the bottleneck for this path. We can't really send more without breaking something, specifically one of the pipes. So that's what F is. And this path we're going to call an augmenting path. Essentially, this path will tell us how to improve our flow. So we're going to augment our flow. We're going to change it using P to create a better flow. So what's our better new flow? Well, that's our F prime here. So this flow F prime is just going to be the original flow F plus the bottleneck value if the edge U to V was in the path. Otherwise, it's minus F if the reverse edge was in the path. And it's the original flow value otherwise. So intuitively, this new flow is exactly the flow F, but changed on the edges in the path. So we make everything else the same. We're not changing the other flow values. We're only changing the flow values on the path. Now again, the second case is a little weird, like this reverse edge thing. That's mostly there for when you have stuff like this, because you could actually have a path from T to S. And what that represents is you're removing flow down that path. So if this is in the residual graph, then in the actual graph, this is saying remove flow from this path. Okay. But for the most part, when you think of this conceptually, you want to think of the first case. Intuitively, this is, the main thing we're really doing, is we're taking some flow from S to T, some path from S to T, and we're literally increasing it. So maybe we're doing F plus 1, F plus 1. That's how you want to think of this procedure. We just add some flow all over that single path in the original graph. Sometimes we might want to remove flow from a path, and that's the second case with the minus F. Okay? So here's a picture representation. So this path in red here is an augmenting path. And so what we're going to do, the 10 here indicates we can increase the flow by 10 on that edge. The 10 here means, again, we can increase it. Now, the issue here is the bottleneck is 5. So although we could increase the flow to 10 on those edges, if we do that for everything, we'll end up breaking some of the capacity constraints. So instead, we're going to use the minimum value. This 5 becomes F, capital F. And so we're going to add 5 units of flow through this path. So let's do that. So we added 5 units of flow there. Now remember, in the original graph here, we were actually sending flow from the top node to the bottom node. So this path is actually, this edge right here is actually a reverse edge. So it's telling us to remove flow. So now you'll notice on this edge, we've removed flow. We had 10, we maxed it out before, and now we've removed 5 from it. Now this one's a forward edge. It existed in the original graph, and so we're adding to it. We add 5 to it. This one is another reverse edge. So this one here is telling us to remove some flow from that edge. Essentially, it's telling us adding flow to that edge was a mistake, and we need to backtrack and undo that decision. And then lastly, we add some flow to that edge. So overall, this is the new flow F prime. And notice it has a larger flow value. So the original had flow value 10, but now this one has an extra plus 5 leaving S. So the new flow value is 15, which is better than 10. So any questions on this? Yes?
Maybe I missed something, but why is that one edge reversed?
So remember, this is the residual graph. In the actual original graph, the edge goes in this direction.
Okay.
So it's literally reversed. So intuitively, what the residual graph is telling us, it tells us when to add more flow and when to remove flow to improve our overall flow. So G of S tells us when to add more flow and when past flows were a mistake, so need to backtrack. So I'm using the word backtrack here specifically to indicate this is kind of like dynamic programming. In effect, this procedure is going to generate all possible flows recursively. But we'll get to that later. I just want to put that into your mind. Okay, so we have this cool F prime here. It seems to be better than our flow F, but is it even a flow? Is it even feasible? So the reason it's a flow, which means conservation holds, I'm going to let that be an exercise. You should all think about why that's true. But the idea is kind of what I indicated before, which was if you just add a path. Where did I do that? It's gone. Here it is. Nope. Here it is? Yeah. So if you have a path, if you just add a path to a flow, conservation holds. It's basically the same idea, but you should think about how to formally prove it. Okay. So let's just assume it's a flow. We want to prove it's feasible. So let's do that. So there's 2 main cases. Either P contains the forward edge or P contains the reverse edge. So if P contains the forward edge, and we want to show it's feasible, we want to show 0 is at most F prime of U to V, which is at most the capacity of U to V. That's what we want to show. Now, if P contains U to V, well, we know the residual CF of U to V is equal to C of U to V minus the flow from U to V. So we know that, and we also know that F prime of U to V, by definition, let's check it, it's the flow from U to V plus F. So the easy part is going to be the 0 less than or equal to part. So let's do that first. Well, this is greater than or equal to 0 because the original flow was feasible by assumption. So the original flow is at least 0. And that capital F is also at least 0 because it's a capacity, right? That was the minimum capacity on the path. So those are both at least 0, and so the sum's at least 0. So that part's easy. So now we need to show the right part. This one's a little harder. So how are we going to do that? Well, we know the definition of f prime. So f of u to v plus f. Now remember, f is the minimum on the path. For any uv on the path. So because f is the minimum, it's at most any edge on the path. So this is at most f of uv plus the capacity of uv. The residual capacity of uv. So now we know what the definition of CF is, so let's use that. So now we have f of uv plus C of uv minus f of uv. So then we can just cancel these two, and that's equal to C of u to v. So this proves that our flow value, f prime, is at most the capacity u to v. And so f prime is feasible in this case. So this implies f prime is feasible for the edge u to v. Any questions on that? Okay, so let's do it again. Now we're in the reverse direction. So now the reverse inequality is going to be easier. So showing it's at most c will be easier this time. So we have f prime of u to v. This is equal to f of v to u. Actually, let me write it like this. F prime of v to u is equal to f of u to v. And just because f is feasible, that's going to be at most the capacity of u to v. Okay, so the reverse direction was the easy one. Now we need to show it's greater than or equal to 0. So f prime from v to u, this is equal to f of u to v minus f. Oh, I forgot the minus f. What? Minus f. So what else do we know about this? Well, f of u to v minus f. This is going to be at least f of u to v minus the residual capacity of u to v, or sorry, v to u. Remember, v to u is the one on the path. So that's why when you talk about things on the path, we have to talk about v to u. But when we talk about things in the original graph, we talk about u to v. So it's a little tricky. So why is this true? This is true because f is the minimum. So we know f is at most cf of v to u. And so negative f is at least negative cf of u. That's what I use there. And now by definition of cf of vu, remember when we use a reverse edge, it's equal to the flow of the reverse of the edge. And so this is just equal to f of u to v minus f of the reverse of v to u, which is u to v, which is equal to 0. Okay? So we know f prime is at most c, the capacity. and we know it's at least 0, and so again, f prime is feasible for this specific edge, v to u. And so the last case, well, if neither u to v or v to u is on the path, remember we don't change anything. Anything not on the path we leave alone. So then f prime of u to v is just the original f of u to v, and then feasibility holds because f is feasible, and f prime equals f. So by assumption, we're done. Okay. So those are all three cases. So now we know f prime is indeed a feasible flow in our graph. So then the question is, okay, we know it's feasible, but is it always bigger than f? So in the example, it was bigger than f, but is this always true? Yes, it is always true. Otherwise, we wouldn't have a theorem to prove. So why is it true? Well, the key idea here is we only change things on the path from the path P. So in particular, the flow value of f prime is the flow value of f plus the new flow value of P, leaving S. So in particular, it's a path, right? So it's only the first edge that affects us. So specifically, this is just the value of the first edge in P. Because the first edge is the one that leaves S. So is this first edge positive? Well, remember, the first edge leaves S. So f prime of S to W, I'm going to say this is the first edge. This is exactly f of S to W plus capital F, because it's a forward edge. And because f is a positive number, this is greater than f of S to W. So we've increased our total flow. So in total, this is the size of f plus capital F, and this is greater than the size of f. So our new flow has bigger value than the old one. So what does this mean? Well, it means f is not a maximum flow. If f was a maximum flow, well, you couldn't find a bigger one. So if there exists a path in the residual graph from S to T, then we know f is not a max flow. Okay? So now let's suppose there are no paths from S to T in the residual. In other words, there's no augmenting paths. So let's assume that's the case. And let's define S to be the reachability set of S. So these are all the things that S can reach in the residual. So basically we run a whatever first search on S and see everything that's marked. And everything that's marked is S. So this is everything marked in whatever first search starting at S. And then we define T to be just everything else. We don't care. Okay? So clearly this is a cut because by definition it partitions V. So now we just want to show that the size of f is equal to the size of this cut. Because if that's true, then by our lemma, we know f is actually a maximum flow. Okay, so let's prove that. So because S, capital S is the reachability set, and by definition, there is no path from S to T. That's our assumption. If there was a path from S to T, that's an augmenting path. So because of these two things, we know there are no edges from capital S to capital T, in G of F. So if we drew a picture, we have S, we have T, and there might be edges from T to S, but there are no edges from S to T. These don't exist. So in particular, we know the capacity, the residual capacity, is 0 for any of those potential green edges. So what does that mean? So by definition of the residual capacity, the residual capacity is either the original capacity minus F, or it's the reverse flow, depending on whether U to V or V to U is an edge. But either way, they're going to be 0. Because by definition, that edge doesn't exist in the residual. So in particular, we know both of these are 0. And so what does that mean? That means we've avoided all the edges. We've avoided all those purple edges. And we fully saturated all the green edges in the original graph. So we have a flow that saturates all edges, U to V, that cross the cut, and avoid all edges V to U that cross from the other side. So our lemma tells us the value of F equals the capacity of ST. So in particular, for any graph, given a flow, we can keep improving it. And by induction, eventually, you've improved it as much as can be improved. And then we have no augmenting paths. And once we have no augmenting paths, we can create the cut. So given the max flow, we can create the cut from the residual graph, and the cut and value of the flow will be the same. So they're both optimal. So for any graph, there exists a flow and a cut with equal values and capacities. So any questions about that? Ultimately, the idea is we start with any flow, which could be the 0 flow, right? So the 0 flow is always feasible. Then we continually use augmenting paths to improve it. And because flows are finite objects, eventually you hit the maximum and you can't improve it anymore. And at that point, you know there exists this cut in the residual. And that cut is the cut we claimed existed. So it's basically kind of an induction type proof. Technically, it's not induction. It's proof by smallest counterexample, but they're basically the same thing. But notice this is basically an algorithm, right? So that's the formal proof, but it gave us an algorithm for free. And really, the algorithm that we built is what proved the theorem. So what's the algorithm? We keep sending flow down an augmenting path, and then we recursively do it again. So we create the new flow, create the new residual, augment it, we get a new flow, create the new residual, and keep going. So in particular, we start with the 0 flow, which is always feasible, and we repeatedly augment the flow along any path from S to T until we're out of paths. And once we run out of paths, either we return f as the max flow, if you want to solve max flow, or you can return st as a min cut. So you're really solving both problems simultaneously. You get the solution of one for free when you solve the other. And this is, we call this duality. So the problems are dual. They're basically inverses of each other. If you can compute x, you can compute minus x easily. And that's basically what this is saying. We have a max problem and a min problem that are kind of related. Okay, so this is called the Ford-Fulkerson algorithm. It's just mimicking the proof of the max flow min cut theorem. Yep.
So just want to make sure, augmenting means like f comma f prime, right?
Yeah. So augmenting is when we construct f prime. So we add f to the original flow according to some condition. So I'm just using the bracket notation to simplify that. Okay. So one other cool thing about this algorithm is what's called the integrality theorem, which is like the thing you're going to use the most when you do flow stuff, which says if all the capacities in the flow are integer, so if you start with all the pipe sizes being some integer, then there exists a max flow such that the flow through every edge is also an integer. So if your capacities are integer, your final flow will also be integer. You won't have like f of e being the square root of 2. So f of e is not the square root of 2 for an e. So why is this useful? You're going to inevitably use flows in graph reductions. And usually when you're doing this, you want to create some objects. Like you want to assign people to internships, say. And in that case, you assign a single person or multiple people to an internship. You can't assign fractional people to an internship. So if you're using a flow and you create a flow with a square root of 2, I don't know how you're going to have square root of 2 people on an internship, but so you need to always be careful that you're creating graphs with integer capacities if your goal is to solve an integer problem. So the proof of this is really easy. It's by induction on the iterations, but the idea is even easier. So we start the process with the 0 flow. Obviously 0 is an integer. And now what do? We create the residual at any point in time. And the residual is either a flow value or it's the capacity minus a flow value. Strictly speaking, let me reverse that. Okay, so if by induction the flow value f is always integer, then we know this capacity is integer in that case. Or we have an integer capacity minus an integer flow, which is also integer. So in either case, these are going to be integer. So we know the residual capacity is an integer. And remember, capital F is the minimum bottleneck. So it's some min over edges of CF of U to V. So that's an integer. And at the very end, what's F prime? F prime is the original F plus capital F sometimes. So some of the edges you add F, some of the edges you subtract F, the other ones you don't do anything. So what's this? Well, it's an integer plus an integer or minus an integer So it's an integer. So assuming the past steps correctly made f an integer, then in the current step, we also get a flow that's integer. Okay? So that's basically the whole induction proof. And you can write it in words, but that's the idea. So any questions about this? Another way to think about it is you're maintaining an integer invariant. So at every single point in the process, you have an integer flow, and you're maintaining that over time. So if at any point in the process your flow is integer, then at the end of the process, it's also integer. It's not going to suddenly like phase transition once you've stopped adding things. So that's another way to look at it. So any questions about the Ford-Fulkerson algorithm and the integrality theorem? So Ford-Fulkerson algorithms, the main thing you're going to be using. So if you do a modification instead of a graph reduction, you're usually going to modify Ford-Fulkerson because it has a lot of useful mathematical properties you can exploit. Typically, the integrality theorem is the one you're going to use. So maybe instead of using any augmenting path, you want to use a specific type of augmenting path to solve whatever problem you're doing. But in general, Ford-Fulkerson is not the best algorithm. So here's the running time. How fast is this thing? It's going to be O of E times the size of the max flow. Why is that? Well, let's just think of like integer flows for a second. Let's say at every iteration, you improve the flow by a single unit. So each iteration, your augmenting path has a flow value of 1. And so how many times do you have to add 1 to get to the max flow? Well, it's the size of the max flow. So it could take size of S star iterations, or you could think of the recursion tree having depth size of F star, whichever you prefer. And now for each iteration, we have to build the residual graph, and we have to search the residual graph. But we can do both of those in O of E time. Technically, it's O of V plus E, if you want to be really precise. But for most flow problems, we're assuming it's a very well-connected network. And so we just treat that as O of E. So it's O of E time to construct GF and then do whatever for search. So we do O of E operations, and we do it that many times, so that's the total running time. Yes? F star is the maximum flow. So this is just saying the value of the max flow. Other questions? So now I'm going to ask you, is this actually a fast algorithm? It looks fast, that kind of looks linear time almost. But is it really? Is it really linear time? Is it even polynomial time? I claim it's not. So here's an example. So here the size of the network, in particular the number of edges, is 5. It's very small. And what's the value of the max flow? It's going to be 2 times x. Because you could just send flow here and here. This is the size of f star. Now you can actually prove that what Ford-Fulkerson will actually do is it'll always take this path for some reason. So it always does the dumbest thing possible. So you could solve the whole problem in one step just by sending flow down the top and the bottom paths. But what it'll actually do is it keeps sending flow on this path. And so in total, it'll actually take this many iterations. Okay? Now let's think about x. So if we think about the input size in terms of bits, so I'm going to call the input size m. These are the number of bits that we have to write down to describe the input. Well, how many bits do we need to describe the whole graph? I don't know, like 10? And then how much for x? Well, x is pretty much the rest of it. So all of m is the complexity of x plus the graph complexity. So typically when we write down numbers, we write them in binary. So this is going to be log base 2 of x, because that's how we describe numbers in binary. So in terms of our whole input size, our entire input is size m, and it has this tiny little piece that's the graph, but most of it is describing x. But in general, maybe it's more balanced. So let's say half of it's the graph and half is x. Okay. So roughly, x is log base 2 over 2. That way, it's half of m. So let's say this is half of m. So normally when we describe algorithms, we describe them in terms of some input parameters. For graph problems, we usually think of the number of nodes. But the number of nodes is not the total length of the input. So the number of nodes is not always even close to the total size of m. So usually if you talk about trees, it is. So for trees, then n is, omega, or it's theta of m. So basically they only differ by a constant. So it's okay to focus on just the number of nodes because it's basically the size of the input. But for these kinds of algorithms, when you have an integer involved, they depend on the value of the integer. So if the number of bits to describe x is m over 2, the actual value of x could be 2 to the m over 2. So I've just raised 2 on both sides. So the value of x could be exponential in the total input size. And this is the point. Whenever you have an integer valued thing in your problem, or any real number, doesn't matter, if your running time depends on the value of the number instead of the length of the representation of the number, which is the log part, this is the length of the representation, then your algorithm's actually exponential time. Because with n bits, you can describe a number of size 2 to the n. So Ford-Fulkerson's algorithm is really exponential time in terms of the length of the input. So these types of algorithms, we call them pseudo-polynomial. These are algorithms where you have a poly dependency of the actual input parameters, like the graph parameters. So we call it like V and E. But then you also have something poly in the value of an integer. So pseudo-polynomial time algorithms are better than nothing, but they're typically exponential in the worst case. So just wanted to warn you about that. You might have remembered the subset sum algorithm we did in DP. It was O of n times t. And t was an integer associated with the problem. It's the target value that we want to sum to. So that algorithm was not polytime. It's actually pseudo-polytime. In the worst case, t, the value of t could be proportional to exponential time in the size of the set. So that's, in the worst case, exponential time. So the takeaway is, if you're running Ford-Fulkerson, unless you know the value of your flow is very small, you probably want to use one of the different algorithms we're going to talk about. However, if you're using a modification of the algorithm, usually you can tweak it so that it's using good flows, good augmenting paths, and so it'll run faster. So just something to keep in mind. And this is generally a difference between DP and general graph reductions. So in DP, oftentimes for complicated problems, you'll have to use some kind of integer dependency on the problem. So like for subset sum, you got that t in there. And usually you can get rid of that by using a graph reduction. So a graph reduction can translate something like O of nt to O of n to the fourth. So the input parameter n gets hit by a lot. That time increases by a lot. But you're removing the exponential dependency that's hidden inside the number t. Now you can't do this for subset sum specifically, but you can generally do this for many problems. In particular, for the racetrack problem on the homework, if you try to use dp and your dp has like a velocity as one of the subproblems, then it's going to be pseudo-polynomial time, which is way too slow. But if you use a graph reduction, you can probably get rid of the velocities somehow. I don't know, just a thought. So any questions about pseudo-polynomial time and, in general, polytime algorithms? We'll talk about this in more detail when we get to MP completeness, but just, I guess, kind of the main takeaway is if you have an integer in your running time, it's bad. That's the main takeaway. Let me just write that. Okay. So now let's talk about an alternate way to look at flows. So up to this point, we've talked about flows as being some function on the edges of a graph, and we want it to be no larger than some capacity and greater than or equal to 0. But we can also look at flows from a purely functional point of view and kind of ignore like capacity constraints and stuff like that. So if we think of it purely as a function, then we can take a flow h, and we can write it as a linear combination of other flows. And this is true for almost any function, right? So it's basically, when you think of a basis of a vector space, you're writing a vector as a linear combination of other vectors. Well, you can do the same thing for functions. And in particular, you can do it for flows. And what's really cool is not only can you write it as a linear combination of functions or flows, you can break them into paths and cycles. So in particular, you can make every f a path and every g a cycle. So what do I mean by a path and a cycle? Here's an example of a path flow and a cycle flow. So specifically, these are paths with value 1 and cycles of value 0. So the picture, which is the real point, is they look like this. So either it's a path from S to T, where every edge has flow 1, or it's a path from T to S, where every flow value is -1. So the other one's a little weird, but the reason why it works is, remember, the value of the flow is the net amount leaving S. So it's the amount leaving S minus the amount entering S. So if the amount entering S is -1, this net change is still 1. So it's just a little trick there to make it still work in either case. Now for cycles, it's basically the same thing. Either your cycle goes in clockwise order or it goes in counterclockwise order, and it's 1 or -1 depending on the orientation. But the important part is the value of the flow is 0 because the amount going in exactly equals the amount going out. And it looks like that, just a cycle. Okay, so any questions on what these are? Okay. So there's this crazy theorem called the flow decomposition theorem that says every single non-negative ST flow can be written as a positive linear combination of paths and cycles. So in particular, all the flows we thought of up to this point have been non-negative. And so we could break all of those down into a bunch of paths and a bunch of cycles. So literally, if you had your graph, you had any arbitrary flow, then you could turn the flow into a bunch of paths that eventually hit T. Maybe they have different values. And you could also turn them into cycles. So in particular, why this is cool is you can think of this as covering all the edges. So every edge will either be on one of these paths or in one of the cycles. And this kind of covering thing is super useful in a ton of applications. We won't go through the applications today, but that's why this is useful. So just ignoring why it's useful for a second, it's also really cool mathematically that you can just turn it into cycles and paths. So let's just focus on that part. Yes?
Why do you need the cycles? Because can't you do like a linear combination of paths to create a cycle? Like, couldn't you just like, if you had something from...
That's true, but the flow values wouldn't work out. So the issue is all the value leaving S. So here's an example, actually. Consider the following ST flow that has absolutely no edges between S and T, but you could still have a flow like this. Actually, it doesn't even have to be 0. It could be like 5, 5, 5. So technically, yeah, you can make this is a path, and the last edge is a path. But those paths don't have unit flow. Each path has to be value 1. So if you broke those up into paths separately, they don't have value 1. They would have value 0. So we want this to be paths with value 1 or cycles with value 0. We don't want any paths of value 0 for this. You should think of the paths as being used to capture all the flow leaving S. So everything that leaves S has to be on a path because it's being created. So you're getting positive numbers. But things on cycles are just zeros. So we only need cycles to capture the things kind of in the middle of the graph. We can always use paths to capture everything from S to T. But everything else that could be there, we need cycles for. Yes?
Can you come up with some sort of an analogy that represents the road network?
Well, the reason I can't do that is because this is usually not done. So like this part. So you can always create an S to T flow that doesn't have cycles. That's going to be a consequence of this theorem. So because of that, you wouldn't actually do that usually. But in order to prove that fact, you first have to allow cycles. So we're essentially going to allow cycles and then prove we don't really need them.
Okay, so is this like why Google Maps, when it's trying to dynamically weight cars so that it avoids traffic, like it tells you to go a different way if there's a traffic jam? Is this the way it doesn't send people in circles until it's put on the road?
No, those aren't flow algorithms. Those are shortest path algorithms usually. Yeah, flow is more complicated. Yeah, so there are reasons you would want to consider cycles, but usually they're not for traditional flow applications like sending resources. It's usually more of edge covering. So if you wanted to cover edges, then this is definitely not, paths are not sufficient. So for example, here's a really easy, this is a great example right here. Right, so this cycle doesn't even touch S or T, so you can never use a path to hit it. A path of unit value. Again, it's important that's unit value. If we allowed paths of 0 value, then it'd be fine, but we're not allowing that. So either cycles with 0 value total or paths with 1 value total.
How does the cycle have a 0 value? I don't understand.
The value of a flow is equal to the amount leaving S. So in this case, it's trivial because it doesn't even touch S. So it has no way to affect the value. But let's say it did include S. So for this example, the amount of flow leaving S is 1, and the amount of flow entering S is 1. So the net amount leaving S is 0. So you have 1 leaving and 1 coming in. So 1 minus 1 is 0.
So every cycle is equivalent to a self-edge that does no good.
It depends on the application. So the thing is, like, cycles are useful when you want to cover edges. So if you had a road network and you want to break it into categories, like these roads are going to be used for construction or something, then if you need all the edges to be covered, to be considered, you need to allow cycles to hit them. Otherwise, if there were no cycles, you could just use paths from S to T. Yeah, so the cycles thing, it's hard to motivate why we need the cycles right now, but just mathematically, we'll just assume we need them, and we'll see in the proof why they come up. So here's the idea. we're just going to induct on the number of edges that have non-zero flow by looking at the Ford-Fulkerson algorithm backwards. So what we're going to do is we have our graph. We're going to take any path from S to T. So we have our path from S to T. It has some amount of flow. It's an augmenting path. And then we're just going to kill it. So we take this path, we construct our capital F, and then we subtract F from this flow. So we're doing it backwards from before. So remember before, we take paths and we add to improve our flows. Here we're doing the opposite. We're starting with like a max flow, and we're continuously undoing all the augmentation. So we subtract F from all these edges, and because that's a bottleneck, we know one of these edges has flow value F. So now that thing has flow value 0. So we have our F is equal to some F prime plus a path times capital F. And so our F prime, which is if we took our flow and removed that path, we know it has one edge with 0 flow because that was the bottleneck. And so this F prime has one fewer edge with flow. And so the induction hypothesis implies we can further decompose F prime into paths and cycles. So then the induction hypothesis gives F prime a decomposition. So F prime's decomposition plus this extra path gives us a decomposition for the whole flow F. Alternatively, maybe we find a cycle. So maybe we try to find a path from S to T, but we end up revisiting a node more than once. So if we revisit a node more than once, we've found a cycle, and then again we just do minus F to everything on that cycle. And that will break one of the edges, and then we can recurse. So in this case, we have F prime plus a cycle times F equals F. So that's the idea. We're using induction to recursively construct a decomposition of the simpler graph with fewer edges. And then we combine that with the cycle or path we found in the first step to get a full decomposition of F prime of F in terms of cycles and paths. So that's the idea. Now to make it formal, you first want to prove it for circulations. A circulation is essentially a cycle. So it's just satisfying conservation on every edge. So it includes S and T. So in normal flows, S and T don't have to satisfy conservation. The source is allowed to generate new things out of nowhere, and the sink is allowed to vaporize things and make them go away forever. But in a circulation, even for S and T, we have conservation holds. So one example is a cycle. So for cycles, conservation holds for every single node. The net output of every node is 0. So this is just like a generalization of cycles. So let's assume we've already proved it for circulations, and you can do that by induction. And it's basically the idea I just said. Now what we're going to do is take our original graph and add an extra edge from T to S. And we're going to give the value of that edge to be the value of our current flow F. So what's going to happen? So S to T, the flow F has value size of F. So the net output of S is size of F. But now we've added this edge, and so we're going to minus a size of F to get a net output of 0. So we took our graph, and by adding a single edge, we've turned it into a circulation. So our original flow has now become a circulation. Now we use the circulation proof to decompose f prime into cycles. And the key thing is, for a circulation, you only need cycles. You never need any paths. So we decompose f prime into just cycles. And then when we remove this edge t to s from the graph, this will break some of the cycles. But if you break a cycle by just removing an edge, it just becomes a path. It won't turn into like another weird cycle or anything. And then the things that don't even touch the edge will just be cycles. They aren't modified at all. So this gives us a decomposition for the entire flow, because we have a linear combination of paths and cycles. And here's kind of an illustration of how you do this for circulations. So for this specific graph, this is a circulation because the output of S is 15, but the input of S is 15. Similarly, the input to T is 15, and its output is 15. So this is a circulation. And then we can break it into 4 different cycles. So we have this big outer cycle. There's this weird intermediate cycle. There's another outer cycle. And then there's a hidden triangle in the middle. And if you sum up all of those different cycles, you get exactly the full circulation. So this is one example of how to decompose a circulation into a bunch of cycles. And all of these cycles have 0 value. Okay? So I won't go through the proof because we're running low on time, but the idea is really easy. Either you have no edges, in which case you can trivially decompose the flow into nothing. So a decomp of the flow is just empty. Or you have a single cycle, in which case it's its own decomposition. That's going to be weird. It's okay. In the last case, what we're going to do is find any walk in the graph, follow a walk starting from S, and remember, we proved in class that every walk contains a path. And how did we prove that? Well, basically, if we start somewhere and we just keep moving around, we either hit T, and so it's a path and we're done, or we repeat some nodes. Eventually, we swing back and hit a node we've already hit before. And the very first time we revisit a node, this is going to be a cycle. So we just keep walking around the graph until we've revisited something. And once we revisit something, it's a cycle. And so we can remove that cycle. In particular, one edge must be removed if we do the -f trick. And then we can inductively create the decomposition on the rest of the graph. And then recurse on the rest. So that's the idea. Now the key thing here is I'm assuming you can keep walking around until you hit a cycle. And why is that? Well, that's because in a circulation, for every node, the net output is 0, which means the amount going in, so if we ever enter a node, because there was positive flow going in, there has to be positive flow exiting. So when we're doing this walk, if we ever follow flow and hit a node, we know there's a way to leave. We'll never get trapped. Even at t, we won't even get trapped at t because we're assuming the whole graph is a circulation. So t also has ways to get back to s. So that's the key thing there. Eventually, this walk will repeat a node. That's the important part. Okay. And as we mentioned before, what we did was we took a circulation and we built it out of cycles only. And so in particular, if we take something, an arbitrary ST flow, we can always cancel all the cycles so that there's only paths from S to T. And we call that an acyclic flow. So in particular, there always exists an acyclic max flow in your graph. It's just a bunch of disjoint paths that end up at T without any cycles in the middle. Okay. So I'll also point out that this is, again, another algorithm. So what is it really doing? Well, we kind of already illustrated it. We either start at S and we find a path from S to T, in which case we do the minus F on the path, or we repeat a node and we found a cycle, and then we can do the minus F trick on that cycle. Every single time we do this, we can just do it using whatever for search, and every time we do this, we remove a single edge from consideration. So we remove at least one edge every time, because we're doing the minus F thing. And so overall, we'll do this O of E times, because eventually we run out of edges. So we do it O of E times, and at each iteration, we only need O of V time to do a whatever for search. So in total, it's O of V times E time. And the reason it's O of V and not O of V plus E this time is because in this example, you can actually prove that you won't hit every single edge. And so you get a reduced time analysis. But I won't go into that. But the thing that should concern you is this problem is harder than computing max flows, yet we did it way faster than we computed max flows.
What do you mean by harder?
So it's a more general problem, decomposing a flow into a bunch of paths and cycles than just finding a single flow. So this problem, not only are you finding one flow, you're finding a bunch of little flows and stacking them together.
So general equals harder.
Usually. Not always, but usually. So because of this, you're probably thinking, well, maybe this can be approved. Like maybe Ford-Fulkerson's not that great, and you'd be right. So in the book, you can actually change Ford-Fulkerson to pick the augmenting paths using greedy metrics, like pick the thing with the biggest bottleneck, or pick the path with the smallest number of edges. And both of these greedy strategies will improve the algorithm. But there's a long line of work of different algorithms. And recently, actually, someone came up with an algorithm that hits O of V times E. So it matches the flow decomposition algorithm. So most people think this is the best we can do. So for purposes of like homework and exams, if you use a max flow algorithm, use Orland's algorithm, and then max flows can be computed in O of V times E time, which is really fast. Any questions?
What's a dynamic tree?
I think a dynamic tree. So there's a theory of algorithms called dynamic algorithms, and they're basically data structures that change over time. So like a binary search tree usually is fixed and advanced. It just has a fixed structure and you can search it quick. But the theory of dynamic algorithms says, okay, our data structures will actually evolve over time. Like new people are added to systems, you get more profiles on Facebook, etc. So can you change those algorithms so that they're still fast even if the tree itself changes? So a dynamic tree is one where you could remove nodes or add nodes, and your goal is to support the remove and add operation so that it's fast over a long period of time. So if you're familiar with hash tables, it's kind of similar where a single hash could be slow, but if you look at it across many hashes, it's overall fast. So that's what dynamic trees are. But the specific dynamic tree algorithm they're using is probably really advanced, so I haven't actually read all these algorithms other than this one. I know the pseudoflow algorithm, which is really cool. Maybe we'll talk about it in a different lecture. But yeah, so if you're interested in flows, there's still a lot of work to be done getting an improved time here. So for the most general class of graphs, O of V times E is pretty much the best we can do. But for special types of graphs, like ones with very few edges, or ones with lots of edges, or like tree type graphs, you can generally do much faster than O of VE. And so there's a lot of open problems there.